In this video, we will discuss the method of radiometric dating. Radiometric dating uses the ratio of parent to daughter nucleotide in order to determine the age of a sample. Now, in order to do this, we need to revisit half-life and the first-order kinetics of radioactive decay. Here we have our first-order integrated rate law and the first-order half-life equation. Now, oftentimes, radioactive isotopes decay is given in half-life, and as we recall, half-life is the time it takes for half of the material to disappear, or to decay, or to react. Now, radiometric dating depends on the ability to determine the ratio of the parent nucleotide to the daughter nucleotide, or the decay product. And there are many different isotopes that can be used for radiometric dating, but it depends on your time scale. For instance, krypton-argon dating is used for things billions of years old, and carbon-14 dating is used for things that are on the order of 10,000 to 20 to 50,000 years old. Now, potassium-argon dating is particularly useful because the decay product, argon, is actually a gas, very easy to trap. Potassium-40 is present in a lot of different minerals. It decays into argon-40 through beta emission and has a half-life of about 1.2 billion years. Now, the concept of a start time, whenever we're determining the age of, in this case, a rock sample, depends on when the mineral that contains the potassium-40 has solidified. Before that, it is assumed that it is completely mixed in magma and that the ratio of the potassium-40 to argon-40 is always constant. Now, once it solidifies, it is no longer being mixed, and now the potassium-40 is decaying, and the argon-40 that is produced is trapped in little pockets. Now, in order to do first-order kinetics, we're going to have to find out what the rate constant K is for this reaction. So we rearrange the half-life equation. We find our rate constant is 5.554 times 10 to the negative 10 per year. Now, in this example, we have a sample of moon rock that was found to contain 78 argon-40 atoms for every 22 potassium-40 atoms. We want to find the age of this rock. Well, as you recall, the first-order kinetics equations talk about concentration. In this case, we can take absolute number of atoms detected as equivalent to concentration. So in the beginning, we have however many potassium-40 atoms are present, plus however many argon. Well, there's no argon in the beginning, but those 78 argon-40 atoms must have come from somewhere. They must have come from the potassium-40. So we actually assume we started with 100 potassium-40 atoms. And in the end, we ended up with 22 potassium atoms. And that's why that is in the numerator. We plug this information into our calculation, and we solve for time. And the units of time are going to be in years. Carbon-14 dating is used for things that are a little bit more recent. What's interesting about carbon-14 is it's actually naturally occurring. Carbon-14 is a product of neutron capture between nitrogen-14 and cosmic radiation. What's really interesting is the rate of decay of carbon-14 is actually equal to the rate of production of carbon-14 in the upper atmosphere by this cosmic radiation. So depending on the material that we're talking about, usually something that's alive, the ratio of carbon-14 to carbon-12, and as well carbon-13, is always consistent as long as that substance is alive. It is constantly taking in carbon and expelling carbon. Now, at the point of death, it is no longer taking in new carbon supply. And the carbon that was there, the carbon-14 that is there, is now allowed to decay, and no new carbon-14 is being added. So this is what makes carbon-14 dating useful. Now, carbon-14 has a half-life of about 5,715 years, and has a natural abundance of about 1 times 10 to the negative 10%. Now, this is not very abundant, but depending on the limits of detection of your equipment, we can actually detect carbon-14. Now the activity, which is measured in curies, which is decays per second, or decays per minute, depending on what you're looking at. The activity of carbon-14 found in this particular living material is 5.58 picocuries, which is about 12.4 decays per minute, or dpm. Now what is the age of a sample of wood with an activity of 7 dpm? Now again, we don't have concentrations here, but we can take decays per minute, or decays per second, whatever the units are, as analogous to concentrations. So again, first off, we need to find out what our rate constant is. Once we have our rate constant, well, if before something starts to decay, or before something is considered time zero, it has a decay of 12.4 decays per minute, and at some time, once it's allowed to decay, it now has an activity of 7.0 dpm. Plug this into our equation again, solve for time, and this particular sample has an age of about 4,714 years. Now it should be noted that carbon-14 dating is never used as the sole determination of the age of a sample of wood or living tissue or formerly living tissue, but it is a very good tool in the arsenal of paleontology, anthropology, and other sciences.